Hello students, in this video we'll begin our discussion of partial differential equations. Suppose that we have a function. We're just going to say it's function u just of x and y. You can do x1 through xn if you want. Let's just make it simple and do two variables, okay? Function u of xy. We say that u is a solution to the partial differential equation okay. So we're going to define what the PDE is now. The PDE looks like this. Looks like f capital of x, y, u. So it depends on the independent variables x and y, the dependent variable u, ux, uy, and you go on and on and on and on. So what you're going to have over here is you're going to have higher order derivatives. Maybe you won't. Maybe you only have ux and uy, but you might have higher derivatives like uxx, for example, or uxy, or uyy, and you can just do higher and higher things, right? So say dot, 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 right? And eventually ends equals 0. We'll say that u is a solution to this if when you plug in for all x and y, when you plug in u and all these derivatives into this function, you get 0, right? If u satisfies equation star. Okay, excellent, equation star. Now that's simply what a PDE is. A PDE is an equation that involves the independent variables, maybe, maybe not, involves the dependent variable u, and then derivatives of u, partial derivatives of u, right? So these are partial derivatives, right? So all these things are partial derivatives. And what we say the order that the PDE star has order n if the highest order of partial that exists in the equation is of order n. Okay, so in particular, you can write down some very simple things. So for example, I'll give you an example of a third order PDE. Here's the third order PDE, ux, y, x plus u squared sine ux is equal to 0. This is third order, right? Because the highest order partial I see is an xy x derivative, third order. Okay, I'm not making any I'm not claiming to be able to solve this PDE, right? But you can sort of get some idea about how you might approach something like that. Okay, so that's a third order PDE. They can be very complicated, right? Good. There are special subclasses of PDE which we're going to talk about. So, case 1, subclasses. Okay. Class number 1 are the linear PDEs, which we love. Okay. The PDE is linear if this function f capital is a linear function in all the variables. So, the linear PDEs implies that f capital is a linear function, is linear in all variables. Okay, good. Then there are semilinear PDEs. Okay, and that says that f is linear in the variables except for potentially the variable u, right? F is allowed to be nonlinear only in the u variable. Okay, so what's an example of a semilinear PDE? One of the classic ones is the semilinear Klein-Gordon as an example of this. This comes up from physics. A lot of PDEs come up in physics. So as a mathematician, I'm grateful for the physicists because they give us all sorts of really fun problems to work on. This is going to be what? This is going to be, I'm just going to do it in one dimensions, UTT. So now here I've replaced x and y with t, right? So now I'm also starting to incorporate some idea of like a temporal idea, like an idea of time, right? Minus x. Okay? If that's just set that equal to 0, that'd be the wave equation. But the cubic sine-Gordon looks like this, plus u cubed is equal to 0. We can see that we're linear in the uxx and the utt variables, and that we're nonlinear in the u variable. So that's the semilinear Klein-Gordon equation. Good. All right, what's the next one to do? The next one to do is the third class is quasilinear equations. Okay? And what quasilinear equations are is you're allowed to have coefficients of the highest order derivatives are functions of all variables up to, so we'll say up to the highest order minus 1. Up to the order of the PDE minus 1. Okay? So what's an example of this? An example of this, we've already seen this in our differential geometry course. We can look at something like this. 1 plus ux squared uyy minus 2 ux uy uxy. And then what? And then plus, what am I missing now? Okay, good. 1 plus uy squared, and then uxx equals 0. This is the minimal surface equation, right? This is the minimal surface equation, which comes in differential geometry for the surfaces whose mean curvature vanishes. And look at the coefficients of the highest derivative. The highest derivative we see is what? The highest derivative we see is second order. And the coefficients of those second order derivatives are all functions of lower order, right? So this ux is, the order of PDE is 2, and so the ux is a first order derivative. I'm allowed to have those as coefficients of these things. So this is a quasi-linear equation. This is the minimal surface equation. Good. All right, and then there's fully nonlinear, which is what you expect. There's nonlinearity everywhere, right? And then that's class 4, is fully nonlinear. Okay, and that's just F is completely nonlinear. And what's a classic example of this? A classic example, this is the Monge-Ampere equations. Okay, Monge-Ampere is the determinant of the Hessian equals 0. So what does this look like? This looks like this. This says that uxx times uyy, there's your nonlinearity, right? Minus uxy quantity squared, there's your nonlinearity again, is equal to 0. And of course I can put some forcing function over here too, if I wanted to, for Monge-Ampere. But that's the Monge-Ampere equations, okay? These come up all the time. Now, with PDEs, I have not made any allusion yet to one other very essential component of a PDE. I'm saying it has to satisfy this equation. I haven't specified the domain on which the equation is true, right? So oftentimes, we specify that x and y are in some set omega, right? If that's the case, I can also impart boundary and initial conditions, right? We can then give the equation boundary conditions So in other words, we'll give you information on a subset on the boundary of omega or initial conditions for PDEs that involve time, right? That might be something in the fact that saying u of x and 0 at time 0, you might be given some function f of x, you might be given some time derivative at x0, might be some other function g of x, and you might be given more and more initial conditions. The higher the order is, the more conditions you're going to need to uniquely solve the PDE, right? So we're going to see in further videos that there are questions as to when the PDE has a solution. When is the PDE well posed in the sense of Adamard? In the sense, when can you find a unique solution? When does a solution exist? When is it unique? And when does it depend continuously on the parameters of the problem? Now, when I say depends continuously on the parameters of the problem, that immediately puts us into a context where I need to understand, what do I mean by continuity? It's continuity with respect to functions. Continuity with respect to functions means that there's some functional analysis that's built into the theory of PDEs. So we have two different approach angles that we can consider now. We can consider the approach angle from a functional analytic approach angle, or we can basically just get our feet wet and try to figure out how to solve some very, very simple linear PDEs or semilinear PDEs or quasilinear PDEs with maybe the occasional reference to a very simple structure of a nonlinear PDE, right? So we're going to really focus in on how to handle some of these simpler situations first, and then later on in the course we'll delve into some of the functional analysis, some of the Fourier analysis that's required to understand these PDEs in different function spaces, because then we're going to have to understand what Sobolev spaces are, what Besov spaces are, all sorts of more complicated regimes where you have to define notions of what a weak derivative is. Very much akin to what we do in ODE when we say, when does an ODE have a solution? We know that there needs to be restrictions on the forcing function for the ODE to have a solution. We have to do the same thing in PD, and there we need to develop ideas of weak derivative to understand what the fundamental solution are, to basically use some of the tools from real analysis to prove that a solution exists. And we'll see those in future videos. Thank you very much.